Hello everyone, I'm Shu Tao Cao. The topic of my presentation is BGP routing policies in ISP networks. My presentation will contain the following 6 subtopics. First, let's get into the overview of BGP routing. The BGP routing can be broken down into 3 parts. Firstly, the import policy determines which routes should be filtered, and it may also append or modify attributes. Next, the router applies the decision process to select the most desirable route. How does the decision process work? Well, the router will go down the list, comparing each attribute in the list across the 2 routes. If the route has different values for the attribute, the router chooses the one that has a more desirable attribute. Otherwise, it moves on to compare the next attribute. For example, as a local preference is the first step in the decision process, we can force the route with a longer path to be chosen over a shorter one by changing the local preference. And the third is the export policy, which determines which neighbors the chosen route will be exported to. As the presentation focuses on BGP policies, let's zoom in to the configuration of local policies. Preference. Preference influences which BGP route will be chosen for each destination prefix. Changing preference is done by adding, deleting, modifying route attributes in the BGP advertisement. Local preference, MED, are the 2 of the most used attributes. Filtering. Filtering eliminates certain routes from consideration and is often done by instructing routers to ignore advertisements with attributes matching certain specified values or ranges. Thirdly, tagging. Tagging allows to associate an additional state with a route and uses this additional state to coordinate decisions. The key mechanism is the community attribute. It is a variable length string used to tag routes. The community attribute is a highly expressive mechanism, lending itself to support a wide variety of complex policies that are difficult to express through other means. There are 3 types of business relationship between ISPs. First is the customer-provider relationship, where one ISP pays another to forward its traffic. Second is the peer-peer relationship, where 2 ISPs connect directly to each other, usually without exchange fees. The third is backup ISP, which is used in urgent scenarios. In business relationships, the primary rule is to choose the customer-learned route first. Why? Because routing through the provider is costly, and sending too much traffic into the peer is unfair to the peer and may break up the partnership. So how can we adjust the policy to give customer-learned routes more priority? First, assigning different local preferences is a way out, as routes with higher preference will be considered first. Usually, the range 90 to 99 will be used for customers, 80 to 89 for peers, and 70 to 79 for providers, 60 to 69 for backups. The other way is using community attributes. For example, B doesn't want A to route through B to C, maybe because B doesn't get paid for this. So for every session, router R3 can fix an import policy that appends the community attribute X peer to any route learned over these sessions. This can indicate that the route was received from the peer. And then B can fix an export policy at R1 and R5. These 2 routers will not export any route with community attribute X peer. In this way, A will not get any route through B to C. Now let's go into policies for traffic engineering. Operators can influence outbound traffic flow by changing local preference and modifying IGP link costs. One common scenario is early exit routing, also known as hot plate routing. The ISP forwards traffic to its closest possible exit point so as to reduce the number of link packet traversed and reduce traffic. This can be done by reducing the IGP cost to the nearest exit. Another common scenario is reducing congestion on outbound links to neighbors and balancing traffic. In this figure, assume that there's lots of traffic going through R8 to R3, and R8 is overutilized and needs maintenance. Here we can assign a higher local preference number for routes routing from R9 to R3 to cope with this problem. Inside the AS, we can do traffic control by AS pending and MED. For example, if B wanted to reduce traffic traversing router R1, it could increase the value of MED attributes advertises to A, causing the link to R5 to become more preferred by the A's routers and thereby decreasing R1's load. For another example, suppose B wishes to shift some traffic from its link to A to its link to C. B can do this by prepending additional copies of its AS numbers onto AS passes in BGP advertisements it sends to A. This increases the AS pass length in these advertisements, which causes routes advertised by C to other ISPs to become more designable in a comparison. Besides, remote traffic control can also be done by changing the community attributes. The third scenario is scalability. Limiting routing table size is one of the major concerns, as overflow can cause the routers to crash. ISPs need to protect themselves from excessive advertisement from neighbors by methods like filtering long prefix to encourage the use of aggregation. Also, protecting other ISPs is crucial. An ISP can reduce the number of prefixes it advertises by using route aggregation. Instead of advertising two adjacent prefixes, like 4.1.2.0/24 and 4.1.3.0/24, they can be filtered in the export policy and a less specific prefix, like 4.1.2.0/23. However, doing this effectively may require knowledge of the neighbor's connectivity, which is not discovered or signaled by the BGP protocol and hence must be manually detected and accounted for by human operators as illustrated in the following example. This is a scenario when a new customer D is added to E. Suppose E owns prefix 6.0.0.0/8. And E has allocated the subnet 6.1.0.0/16 to R5, and we can discuss the question in three situations. Suppose D has a sole provider E. In this case, we can apply aggregation securely and no new advertisement is needed. It just adds a statically configured route at R5 to forward all traffic in 6.1.1.0/24 to D. In the second situation, suppose D connects to two routers, R5 and R6 in E. In normal cases, both R5 and R6 need to advertise the prefix 6.6.1.0/24 within E, so all routers within E know they can reach D via either R5 or R6. Here, E can aggregate the advertisement into its address space. This is done by configuring R5 and R6 to tag a community attribute onto advertisement of prefix 6.1.1.0/24 and configuring all border routers to filter routes with that community attribute. In the third situation, suppose D connects to both E and F. In this case, aggregation by E is forbidden. If it did, Then F will then be advertising a longer prefix route to reach D. Since routers use the longest prefix match, all routers on the internet will prefer F's route over E's route. This problem can also be addressed by adding a community attribute as we discussed in the last situation. Another issue in scalability is to limit the number of routing changes. This can be done by flapdam. Flapdam works by maintaining a penalty value associated with the route, and the penalty value will be incremented whenever an update happens. When the penalty surpasses the threshold, the route will not be selected for some time. The last topic is security. First, discarding invalid routes is important. This can be done by the method of filtering. ISPs protect their customers from learning invalid routes by performing sanity checks to ensure updated contents are valid before propagating them internally. Invalid routes will be filtered. Second, ISP need to protect the integrity of routing policies by rewriting attributes. For example, suppose the ISP in Champaign pairs with a neighbor in both New York and Chicago. By advertising a prefix with the MED of 0 in New York and MED of 1 in Chicago, the pair could trick the ISP into having all of its routers direct traffic for this destination through the New York peering point, even if Chicago is much closer. To defend against violations of peering agreements, the ISP can configure the import policy to delete attributes or override them. For instance, the import policy could set all MED values to 0. Third, blocking denial-of-service attacks, which can degrade service by overloading the routers with actual BGP update messages. To protect itself, the ISP can configure each BGP session with a maximum acceptable number of prefixes, tearing down the session when the limit is exceeded. And the import policy should filter prefixes with large mask lengths. Lastly, export filtering can also help secure the network infrastructure. Here comes the conclusion. The diversity of policies made it possible to deal with multiple scenarios, but this can also lead to misconfiguration, oscillations, and protocol divergence. Plus, BGP also suffers from difficulty in the communication of different protocols, so there are still some future investigations in the areas like configuration checking, language design, new architecture, and etc. Here's my references for this presentation. That's all for my presentation. Thank you.